Okay, so two quick videos here to very briefly go through the guts of Chapter 4. So Chapter 4, Section 4142 talked about our real number system, how to organize numbers on a number line. So you basically should do a little bit of practice on that. I don't have an example here on this sheet. And then the other part was talking about how our real numbers are divided into two parts, rational and irrational numbers. So you really need to remember that irrational numbers are numbers that, color here, numbers that don't repeat, and they don't terminate. Oops, not terminate, terminate. So they don't repeat, they don't end. A couple of key ones that you should remember that fall into this category, our favorite number pi, as well as the square root of 2, both irrational numbers. So our real number system has two parts, rational and irrational. The irrational numbers don't repeat, don't terminate. After that, well, in our rational number system, we have three other parts that we also need to be wary about. So all of these numbers are rational, but within that rational set, we have what we call natural numbers. Oops. Natural numbers. Sometimes just the number set is referred to as an n. These are 1, 2, 3, and so on and so on. We have whole numbers. As a W is our number set, which now includes 0, 1, 2, 3, so on and so on and so on. We have integers. Integers. Capital I. Well, these are our negative values. So smaller than -3, -2, -1, 0, 1, 2, 3, and so on. Okay. All of three of these sets, though, no fractions, no decimals. And then after that, we have, well, the big group, which we now collectively call rational numbers. These numbers include your decimals, your fractions, your long digit numbers. For example, -5.37. 3 over 4, and many more. Okay, so you need to remember there's two parts of our real number system, irrational numbers and rational numbers. Our irrational numbers do not repeat, do not terminate. Okay, some examples, pi and root 2. And then our rational numbers are all the rest, but within that rational number system, we have three different types, natural, whole, and integer. Just be wary of what each of those are. Then it went into, or chapter 4 went into simplifying radicals, so manipulating radicals from entire radicals to mixed radicals. It's like reducing fractions, or having not reducing fractions, but having fractions that can be written as whole fractions or mixed fractions. So same kind of idea. So simplifying radicals, if you're asked to simplify radicals, here our first example is the cube root of 16. The first thing we would need to do is to prime factorize 16. So go through whatever process it is that you need to prime factorize 16 so that you can see all of the lists of prime factors. Okay. I picked some easy ones here so that you may not have to do that step, but that would be the first step. The next step is we would write our root sign. Don't forget that little mini 3 there. If you don't have that, then you're changing the question. So this is the cube root of 16, which is the cube root of 2 times 2 times 2 times 2. Because I am looking for the cube root, I look for groups of 3. There's my group of 3. Well, this lone 2, when I go to my next step, comes out of my radical. And then I write down what's left over. So I still have the cube root of, well, what's left over? This lone 2. I simplified the cube root of 16. Square root of 125, same process. Prime factorize 125, which is 5 times 25, 5 times 5. So this is the square root of 5 times 5 times 5. Okay. Hopefully you're starting to be able to do that process fairly quickly now. I know that there is a tiny little 2 here that I never write. I never write it for the square root of 2, but it's there. So I'm looking for groups of 2. Here's my group of 2. This comes out of my radical sign as a 5. What am I left with? Just root 5. Simplifying those two radicals. Writing as entire radicals. Well, now we need to take that process. Now we have our mixed radical here, and we want to work backwards to get to it look something like this as a whole radical. Okay? So what we have to kind of think in our head was, well, where did this 3 come from? The 3 outside the radical had to come from some kind of group inside the radical, but a group of 3 individual 3's. So I'm going to write, well, I have the cube root because that's what my root is. This 3 to come out of the radical, inside the radical had to be 3 times 3 times 3. Why 3 of them? Because we're doing the cube root. And then we have our leftover bits times the cube root of 2. Now because those radicals are the same, it's the cube root radical, I can put them together, I can combine them. There's my cube root. And what is in the inside? 2, no, sorry, I'm going to start with the 3's because that's what I have written first. 3 times 3 times 3 times my 2. So that's on the inside of the radical. Now I very simply just go 3 times 3 is 9, times 3 is 27, times 2 is 54. Don't forget though, because I'm doing the cube root, this still has to say cube root. Because if it doesn't, you're completely changing the question. Write as an entire radical. 5 fourth root 7. Again, remembering, well, this 5 had to come from some group inside a 4th root radical. That's going to give me a 5. Well, that's the 4th root. There had to be 4 5's in there. 5 times 5 times 5 times 5, and then my leftover bits was a 4th root of 7. 4th root of 7. Of course, we're multiplying those together. Because the radical or the root sign is the same, I can write one root sign, and I can put everything on the inside. 5 times 5 times 5 times 5 times 7. And then mathematically work that out. Well, 5 times 5 is 25, times 5 is 125, times 5 is 625, times 7 is going to be 4,375. I hope, of course, if I did that correctly. Okay, so that's writing your mixed radicals and entire radicals. You need to be able to do those or perform those back and forth. And then chapter 4, 1 and 2, fractional exponents. Now the first part of the fractional exponents, we just talked about how fractional exponents and radicals were kind of related, and how you can work backwards between radicals and fractional exponents. I used to use, or I still kind of do mention, obviously, something termed flower power. Flower power is just a term that helps you to maybe remember that if you have a fractional exponent, that fractional exponent, let's just say that exponent is 2 over 3, not 2 over 2, 2 over 3, that fractional exponent, the numerator, the top part of that fraction, is my exponent, and the bottom part of that fraction is my root. Okay, so it's called flower power because flowers are always got their flower on the top, and then of course their roots on the bottom in the ground. Okay, so knowing that, let's look at 4 to the power of 1/2. Okay, 4 to the power of 1/2 can also be written as the square root of 2 being the root. I don't have to write this 2, right? Remember, I don't have to write this 2. But the square root of 4. Well, square root of 4, well, we know is 2. Oops, not 4, 2. Okay. Now, when we get into fractional exponents that don't have a numerator of 1, really what we're doing here, and you've seen this already, so this is also actually going to be the fourth root, or the square root of 4 to the power of 1. So there's my flower. Here's my root. So there's the flower power. Okay, so remember that those are there. We just generally don't write the 1. And when we're going for quick steps, well, that's what it looks like. But also remember that I could write this as the square root of 4 all raised to the power of 1. So really there's two ways to write fractional exponents. One with the power on the inside of the radical, another with the power on the outside of the radical. Okay. 32 to the power of 1 over 4. Well, if we follow this all the way through, this is going to be my root, my radical sign, 32, of course, all raised to the power of 1. Well, the power of 1 I don't need to worry about because it doesn't change anything, so I can get rid of it, and that's why you generally don't see this step, because anything raised to the power of 1 is just itself, so we don't have to write it down. So now I have the fourth root of 32. I go through that whole process before, prime factorize, get some numbers. This is going to work out to the fourth root of 2 times 2 times 2 times 2 times 2. It's the fourth root. I look for a group of 4. There's my group of 4. This brings out a 2. What am I left with? Just another lone 2. Fourth root 2. Okay. Last one, 27 to the power of 2 over 3. Remember that this is the flower, this is my exponent, this is my root, cube root of 27 to the power of 2, or cube root of 27 to the power of 2, inside or outside the bracket. Now, from here, you need to start thinking about where you want your end product to be. I don't like dealing with big numbers, so if I can keep my numbers small, I'm going to. Because I've done so many of these, I know that there is a nice even cube root of 27. So I'm going to try and find the cube root of 27 first and then square it. You could square 27 straight out of the start here and start working with the cube root of 729. But that's a big number, and now you have to prime factorize 729, which goes on for quite a while. Okay, a whole bunch of 3's. But that's your choice. Either way, you'll still get to the same place. So the cube root of 27, I know, is also going to be the cube root of 3 times 3 times 3, and then of course all squared. Now this is a group of 3. Because it's cube root, one of them comes out. I have no leftovers, the root sign is gone, but I still have my power of 2 here. 3 squared is 3 times 3, which is 9. Part 1 video, side 1 of the chapter 4 review sheet.